Hello. Let us continue with Ohm's Law, power, and energy. We talked about Ohm's Law already because we saw that is a law relating a material with its resistance with respect to the potential or voltage and the current going through it. Okay? So in other words, voltage equals the amount of electric current that can go through a material. We also said that if the material has very low resistivity, it's called a conductor. If it has very high resistivity, it's called an insulator. And if it has some conductivity, it's called a semiconductor. We also talked about power, which we said it was energy divided by time, or joules divided by second, or watts. And we talked about energy, which is joules. So today we will go into these concepts with examples and looking at some specific things within each concept. So for instance, first thing we want to declare are the goals, and we want to be able to recognize the importance of Ohm's law for circuits, either DC or AC, even though right now we're just going to talk about DC circuits. And we want to see how versatile the concept is for different situations. We want to be able to plot voltage versus current for different circuits or for different resistors or for different applications. And we want to be aware the difference between power and energy because they are related but they're different. And sometimes you might need to talk in terms of power, and sometimes you need to express your circuit in terms of energy. Lastly, we want to be able to identify elements such as thermistors and photoconductive cells and thermal resistances, etc. So let's review Ohm's law. The source, a DC source in this case, is called E, energy source. And we said that E is going to be the amount of current going through a material. In other words, the resistance of a circuit can be determined by the potential divided by the electric current. The units of the resistance is going to be ohms. And we mentioned that if you have a voltage going across a resistor, when you have a voltage going across a resistor, this is often called a voltage drop. And it's going to have, for circuits in series, is going to have a voltage difference between before and after the resistor. We will see more about this in an example. Also, it's important to recognize that the voltage is polarized, so you need to be careful and recognize if your voltage is going from your positive when you declare your sign, if it's going from positive to negative or if it's going from negative to positive. This is truly important when we come to see more complicated circuits, when we have to find the currents and the voltages. This declaration of signs will help us determine the values of the currents. So if you look at this example right here, we have a source. This could be a 12 volt source, whatever, a 50 volt source, is depending on the application. The concept is that you have a source, you're gonna have conductor wires, usually copper or silver. If it's a very high-end application, could be gold, kind of like a smartphone where you have gold going through your circuit. And the electric current is going to flow from your source back to its source, traveling through a load. This is called load or a resistor. But this could be also a motor, could be a pump, could be a light bulb. The important thing to recognize is that there's going to be a voltage drop in this circuit in series when you're going from your source to your ground. In other words, if this is 12 volts, you'll have 12 volts here, and then you're going to have 0 volts here because you're connected to ground. The first thing to recognize is that you never want to connect your positive and your negative together before, if you don't have a load. In other words, it will be a bad thing if you did this. This is not safe. You can damage your equipment, you can get hurt, you can do something that could catch on fire stuff, because all the current is going fast to your ground without having a way to dissipate the load. Okay, so um, so this is wrong. The correct way is to connect your positive to a load and your negative to ground. And this is because this load is going to do either mechanical or electrical work. So if it's a light bulb, it's going to turn the light on. If it's a motor, it's going to start rotating. If it's a pump, it's going to start pushing. So recognize that you never want to connect your positive to your negative if you don't have a load. That's why when you work on electric circuits, it's important to unplug your load, unplug your source, so that you can move things around, because a lot of times when you have things plugged in, these two wires, the positive and negative, can touch, and then they can cause a spark, or something bad could happen. In fact, I'm sure you've seen when electricians work in AC voltage or high voltage applications, they turn the breaker off so that this whole thing is out of power, and then they can move things around, and if one of those wires touches the other wire, then it's okay. So let's see example 4.3 from the book. Calculate the current through a 2 kilo ohm resistor if the voltage across it is 16 volts. So they're saying the voltage drop across it is 16 volts because there's only one resistor. If there were multiple resistors, then it would be different. Okay, and we'll see that later. In this case, they're basically saying, hey, we have a source that is 16 volts. Why? Because the positive end is 16 and the negative end is 0. Okay, and this is 2 kilo ohms. They're asking what is the electric current. So it's very simple. We just have to find the current from this equation. So current is equal to the source divided by the resistance, and that is 16 divided by 2000. Okay, and then this is going to be 8, this is going to be 1000, and then this is going to be very small, so 0.008 8 milliamps. Okay, so this is a very small current, even though you have quite enough voltage to perform a lot of stuff. So 16 volts is enough to light bulbs, to have motors running, but the thing is that we have a pretty high resistance, 2 kilo ohms. This is 2000 ohms. Okay, so this is how you apply Ohm's law and how you find your quantities. If they gave you the current and the voltage and they told you find the resistance, it will be the same thing. Simply use this equation to find your quantities based on Ohm's law. Now, let's talk about ground, because the concept of ground is pretty important, and also because ground is often used, but in DC circuits, well, in every circuit, there's also another concept called common. And the difference between ground and common is the following. Let's talk about ground first. There are mainly two types of grounds. There's earth ground and there's chassis ground. And the symbols are like so. Okay, so for a circuit such as this, where you have your source, your load, and then you have conductors connecting the load to the source, to the load, this in theory is correct, but it's missing the point where you need to connect to ground. Because if you don't connect to ground, this is not going to be in reference to 0 volts. Okay, so the moment you connect to ground, this is reference to 0 volts. If it's not connected to ground, this could be a different potential. This could be at 10 volts and this could be at 20 volts. This could be at 20 and this could be at 10. Because the ground is what is going to make every voltage go back to 0. So that's the important part of having a circuit grounded. Now, this one is correct because we have the circuit connected to ground. So this is the true representation of the circuit. This one is also correct, even though it's usually not shown. This is mostly when you have a drawing for architects or electricians ready to implement this in a house or a building, where you have your ground. This will say your panel, and then you can actually visualize the ground going to a rod outside the building or the house, where all the grounded wire is connected to the earth. So this is how actually looks in representation of the circuit. The ground from the panel is going to be either a green wire or a black wire or something, and those wires are going to be taken to a rod, a copper rod, that is going to be sticking out somewhere around the house. This circuit is also okay because it's basically saying that these two points are ground, and it's basically saying that they could be connected. So this one and this one is basically the same thing. Okay, so this is correct. In fact, a lot of drawings will have this instead of having a bunch of wires going back and forth because it could be confusing. You simply know, oh, okay, all my wires here go to a ground, and the truth is that a circuit, when it becomes pretty large, is going to be a bar with all the grounds running to it, you know. So when you have a ground symbol, it simply says, okay, I'm going to plug in my wire to one of those. This one is also correct. This one is basically the same as this. This one was same as this, and this representation is the same as this. This one is also correct. It's showing the actual copper rod connected to the ground. This one is not correct because it's not showing that this one needs to be grounded. This one is not. This right here would be not, it would be an open circuit. This would be an open circuit. You need a wire either to be okay, you need a wire either from here to here or connected to ground. As we said, the difference between earth ground and frame is that earth ground will eventually go to the dirt, to the grass, you know, it's a copper rod that it will go into the ground, the actual ground, versus the frame or chassis is, I don't know if you've seen, like when you have a motor and then on the side of it there's like a wire with a screw and with a washer, if I'm able to draw all those things. So you have your power, positive, negative, and then a third wire connected to the casing or the frame or the chassis of the pump or the motor. This is the chassis ground. And this ground is connected to this ground. Okay? And eventually all grounds go to the earth ground. So another important concept is understanding why loose grounds are dangerous. As we said before, you never want to connect your positive or hot line to your ground. When you have an AC circuit or a circuit with a lot of power, this could be dangerous because you could have 30, 50 amps jumping, and there would be a pretty bad spark and it can electrocute you. So if you're going to work with circuits, mostly if you're going to work with AC circuits, you should always turn the breaker off or unplug the circuit. Even with DC circuit, if you're working with circuits that have more than 1 amp and above, you should disconnect your power source. So let's go back to the concept. We know that if we don't draw the ground, it's because we want to simplify the drawing, but it should be a ground to make the drawing correct. But the source or voltage source could be a battery or an actual voltage source that we buy at the store. We have our current defined by us going from positive to negative. And then the voltage drop happens when the voltage goes across the load. And this will have two things. One, it's gonna transfer power to the load. If it's a light bulb, it's gonna turn the light bulb on. If it's a motor, it's gonna move the shaft, and it's gonna generate heat. Okay, so that's why it's important to realize that if you don't have the right sized capacitor, this could also break your circuit. If you have, 200 ohms, sorry, if you have 200 amps going to one very small capacitor, this could be pretty bad. You need a fuse before or something. But the concept is that there are going to be two things happening. One is that power is going to be transferred and something is going to happen to the load, if it's a light bulb or a pump, as we said. And the other thing is that heat is going to be generated. And this is the loss because no system is 100% efficient. So the loss is presented in heat. In fact, for those of you who like NASA stuff and space missions, the circuits, even in the 60s, when the first shuttle one was sent to space, to the moon, the interesting thing is that since in space there's no air, you might ask, well, what do you need air for? Well, if we generate heat, the air is going to cool down the circuit. It's going to carry this heat away. So for instance, that's why computers and a lot of circuits we have small fans so that we can blow air and cool down the circuit. But in space, there's no air to cool down the circuit, and if you have a fan, it's not going to move air through the circuit. So what they did for those missions, and they still do, is underneath the wire, kind of like a PCB. You recognize a PCB, correct? A PCB is usually a green or red board with a lot of small wires that have all the circuit, like for a computer or like a motherboard, like a phone. Those boards with all the circuitry built in, those are PCB. It's a circuit board, printed circuit board. Printed circuit board. And your computer, for instance, needs a fan to cool down the heat generated by the load. Well, for the shuttle and space missions, you don't have that fan because you cannot move air. So what they do is that underneath the conductor, the wire, they have a channel of liquid nitrogen that will flow underneath, which is pretty cold. Liquid nitrogen could be up to or down to -80 Fahrenheit. And it will cool down the circuit with the liquid nitrogen. So pretty cool stuff. Anyway, so that's how we remember that after a voltage drop, you will always have transfer of energy and you have some heat. Okay. Since we only have three variables in Ohm's law, which are voltage, current, and resistance, this is the only configuration that we can have. Okay, the only three equations that we can get from Ohm's law are these. So you can only find a current, a resistance, and a voltage. And we're gonna see that when we have a lot of resistors, we're gonna find what is called the total resistance or the equivalent resistance, so that we can find the current and voltages through the circuit. Now the power can take a few shapes, but it's exactly the same thing. And this is because when you get V equals IR, and say you don't have V but you have IR, the equation for power is P equals current times voltage. That is the equation. But if you don't have your voltage, then what you do have is your current and your resistance. Either you find the voltage and then apply this formula, or simply plug in I times R in here, and that will give you I squared times R. And the same thing, if you don't have current, then you have V divided by R, so it will give you V squared divided by R. So don't get confused. What I do, so that sometimes it's just faster, I find Ohm's law, my quantities, and then apply the P equals IV equation, which is electric current times voltage equals power. So Ohm's law is this right here, V equals IR, and power equation is P equals IV. Okay, those are the two equations that you will need to memorize for this course. Example, what is the power dissipated by a 5 ohm resistor if the current is 4 amps? Very simple, we have resistance and we have current. If we look at our equations, it will be this. So power is current squared times R. So 4 amps squared times 5, that will be 80 watts. Okay, 16 times 5. All right, let us look at another example. So this example says we have an electric motor, and in this case it's a DC motor, and the input voltage is 120 volts and it consumes 5 amps. Okay, so that circuit is something like this, or you can have the motor even. So this is 120 and this is 5 amps. It's telling us to find the power, and this is cut off here, but it's basically V equals the voltage times the current. We have everything, so it's simply 120 times 5. This is 600 watts. So this is a 0.6 kilowatt motor. And notice that in this case we have 120 volts DC. If the motor was 120 volts AC, then it would be different, because now it's a sinusoidal wave, and when you see your AC class, you'll see that now you need the average, or it's also called RMS, root mean square, and it's just simply multiplying 120 by the root mean square. So don't worry about that right now, just be careful, because the power has to be DC in order to apply this formula right here. If it's AC, it would have to have some other constants before. So let's look at the example that we did before. In this case, they're giving us, instead of 16 is 9 volts. So determine the current from a 9-volt battery with a 2.2 ohm resistor. It's 2.2 ohm, not kilo ohm, it's only 2.2 ohm. So the current could be pretty high in this case. So let's use our software tools to do that. Let's plug in the mouse. So first thing we're gonna use is multisim. Okay, multisim. So remember, you create your account, it's for free. You use your college ID, go to multisim.com and then create circuit. And it's very simple. Here's when you play your simulation. These are the probes and the ground, the sources. We're gonna use a source. We're gonna use a DC voltage source, not a current source, but a voltage source. And we're going to use a resistor. I'm going to use R to rotate, or the mouse. And this is 9 volts. Double click to change it here. Double click to change it here. This is 2.2 ohms. And then we simply connect the circuit. Okay. And then ground. And here it could be fine. All right, we just need a probe, and we're gonna say a voltage and current probe. So the voltage is going to be 9, and the current is going to be from Ohm's law, V equals IR, and we already have R and E, so we would simply divide your voltage by your current. So 9 divided by 2.2, and that will give us 4 amps. All right, so this is how you create the circuit multisim. Very simple. Now, if you measure the voltage here, is going to be 0. Look at that. The current is going to be the same, 4 amps, but the voltage is 0. Why? Because this is the ground, is the 0 potential voltage. When you measure voltage, you're measuring a difference. So 9 volts is the difference between your ground and your positive lead. And the second concept that is important to remember, this is a quiz and even midterm question. In series, a circuit always has the same current going throughout. Okay, now we're gonna do the same thing, but we're gonna use Tinkercad. So Multisim is from NI, National Instruments, and Tinkercad is from Autodesk, which is a company that makes software. So let's do this on a breadboard. Okay, and we're gonna use 9 volts, so we can use a 9-volt battery. It's right here. And also with R, we can rotate the battery. So we have, so how does the breadboard work? There are a few things. This row is connected, so any of those points are called nodes, and they have the same connection. So this point here has the same value that this point here. So if you connect this point here, we're gonna use red for power in. Now all this rail has power in. And for power out, we're gonna connect to this rail with a black wire. Now all this rail has power out. So now we have power going through here. Okay. And now often what people do is that they connect both rails so they can get power from the top rail and from the bottom rail. And the bottom rail is positive to this bottom rail here. And that will be red. All right. So they tell us that we need 2.2 resistor. So first of all, we're gonna find a resistor, and it's gonna be connected to power. So here is fine, and it's gonna be 2.2. Very nice. And then we are going to connect this resistor to, so all these points are connected. They're the same node. We're gonna connect this point to ground. Now, the difference between common and ground is the ground is your 0 potential voltage. Common is simply a return line from all the circuit returns. So for instance, if you have a circuit where you have 24 volts, and then you have also 24 volts for sensors and 28 volts for instruments, like opening and closing valves, and 30 volts for data acquisition. All those potentials have different values, obviously 24, 28, and 30, but the return will be um, 0. So in that case, they can connect to ground. But if you have another one, when you have 24, 28, 30, and then you have a motor that goes forward and backwards. And to go forward, you're going to apply positive 10, and to go backwards, you apply negative 10. In that case, ground will be still 0, but your common for that return, in the second case, it will be negative 10. So negative 10 will be your common returning to your circuit. So the difference between common and return and ground is the ground is always connected to a 0 potential, versus common is the return of a circuit. So in many cases, ground could be common. All right, so this circuit is ready to be used. We are not measuring anything, so we need to bring a multimeter. Multimeter. Notice that in this particular case, our ground is our common, right? You don't connect ground to a breadboard. But when you apply this concept to a PCB, you will connect your PCB to a ground. This is only for prototype. Okay, so our positive lead, we're going to measure voltage. We're going to measure our, the question was to measure current. Okay, so let's first let's measure voltage. And to do that, we simply apply here and here. Okay, so 5.35. This is 2.2 ohms, and wait a second. If we apply from here to here, 5.35. Okay, notice that this is because we're not connected to ground. Okay, so what we need to do is measure our current with, remember, to measure current, we need to apply our circuit in our multimeter in series with the circuit. So we're going to apply, we're going to have resistor here, and we're going to have our resistor here, our multimeter here. Okay, so this might be confusing us. We don't need this and we don't need that. We're only connecting to here. Okay, so we're measuring from power before the resistor. If this is confusing you a little, it's just basically doing this. From here, going to the resistor, then to the, from the positive ground lead to your meter, to meter to resistor, and resistor to your common. Okay. Okay, so 9 volts. There you have it. Now if we measure amperage, we're gonna have 2.43 amps, which is not correct. Let me see something here. If you measure amps, 6 amps. If you measure amps here, six amps. I'm gonna have to use a calculator now. Calculator. So we have a 9 volt equals IR divided by 2.2 equals 4 amps. Yes. Oh, okay. I know why. Yeah, it's because of, let me see. Hopefully I know how to fix this, because we should be getting 4 amps. Let me change this to a power source. Power supply, power supply. And then we're gonna connect voltage 5. No, voltage 9. Okay. And okay. And then we're going to do the same thing here. This is gonna be black because these are common. And then we're gonna connect our common to ground, to return our resistor like so. Okay. And then our meter in series. So here to here, and here to here. And this is red. Okay. 4.9. Okay, good. So, the reason why it wasn't working before, which is not very intuitive, is because the battery cannot give you that value of current. In fact, before was giving batteries can only give you milliamps. So we needed to have a power source. So the problem has some typo there that they say use a battery. That's not possible. You would have to get this type of current, you would have to use a power supply. Either the problem has to say power supply, or they change to a 2.2 kilo ohm resistor because it will be a milliamp current value. And milliamps is what the battery can give you. Okay. Back to this. So we found with Multisim and Tinkercad that our current is 4.9 amps, so pretty high current. This current can kill you, so be careful. Also, if the resistor was 2 kilo ohm, 2.2 or 2,200 ohms, then you could have used the battery for this because it will be a milliamps. Now it's 9 divided by 200, 2200 ohms. But in this case, you have to use a power supply because you can get higher values of current. Now, in order to plot voltage versus current using Ohm's law, it all depends on what resistor value you're using. So if you're using, evidently, if you remember V equals IR, or equals R times I, so the slope is given by the resistance. So if the resistance is pretty high, then you're going to have small values of current for a high value of voltage. But if the resistor is 1, then it will be a 1-to-1 slope, right? So like 5 amps will happen at 5 volts. You can see 5 and 5. So it's very simple. If you want to plot your resistance, it will basically be depending on the value of your resistor. And that is because your slope is given by your value of the resistance. As I said, if you have a higher resistor value, then you're going to have less current for a higher voltage. But now, semiconductors, for instance, have a nonlinear representation of voltage versus current. And they have something called the bias voltage, and then they have a point where usually a 0.7 volts where they start increasing the current significantly. Okay, so and that is very useful because once you how do you say this? Once you achieve that point, once you are able to get to the point where you, say if you talking about a PNP transistor, once you're able to close your gate, then you have a huge amount of current going up for a very small amount of voltage. So this is excellent for a lot of applications where you simply need to close a gate for a lot of current to go through. So it really depends on what application you need. So from Ohm's law, you have a linear representation, but from some non-passive elements such as transistors and amplifiers, you have a nonlinear relationship. So remember, the passive elements are resistors, capacitors, we haven't talked about these yet, inductors, we haven't talked about these yet, and diodes, which we haven't talked about them either. Those are passive. Active are mainly transistors and amplifiers. And amplifiers also have a nonlinear relationship between your current and your voltage. Now, it is very useful to talk about energy in terms of kilowatt hour. In fact, that's how you get charged for the energy you use. And remember, if power is energy divided by time, if you multiply by time again, then you're back to energy. So the time is in hours now instead of seconds. So what's hour is basically your power times the amount of hours that you use your equipment. Kilowatt hour is the same thing, your power times the time in hours divided by 1,000 to give you a kilo unit. So for instance, in this example, say, calculate the electricity bill if the reading was 4650 kilowatt hour and the average cost is 11 cents per kilowatt hour. So this is very simple. The month before we had 4650 and now we have 0. So we have 0, then we have 5, then we have 3, 6, 0. So 5360. 5360 minus 4650 is 710 kilowatt hours used. And was 12 or 11? This must be a typo, 12. And they're saying that is 12 cents per kilowatt hour. So 710 times 12 is basically 85 times $2. Sorry, $85.2, $85.20. So this is pretty much how you do with that. When you look at your bill, they will tell you how much is the kilowatt hour consumption for the month, and you simply multiply that for the amount of cents that they're charging you per kilowatt hour. Now, efficiency is another important concept, and efficiency is basically the energy input is equal to energy output plus the loss. Usually, energy input is higher because since you have loss, then you have a lower energy output. As we said before, in the case of a circuit, when you have a power source and you have a load, some of this will go into the load, but some of it will also go into heat, which is an efficiency. Unless you're using a heater, which and even in that case is not 100% efficient because it will lose some power through the resistors and the resistances. Your circuit is not 100% efficient. It's just based on the second law of thermodynamics, which is entropy. Um, basically, is the ratio between the heat and the temperature. But anyway, this is thermodynamics more. If you're interested in this part, you just look at second law of thermodynamics. It will tell you why you cannot have a 100% efficient circuit all the time. But the way to compute it, efficiency, which has this eta symbol, Greek letter, is the power input divided by the power output divided by the power input. This is a percentage. Since the power input is higher, this will be less than 100%. And the concept is that when you have energy input to a system, some of it will go to your output, what you want, and some of it will be stored in your system if you have capacitors, etc. And some of them is gonna be lost to the ambient by heat or by inefficiencies, etc. For example, a 2 horsepower motor operates at 75% efficiency. what is the power in watts? If the applied voltage is 220 volts, and what is the current? So very simple. The first thing is that they're giving us the efficiency. So we should be able to compute from this equation, we should be able to compute from horsepower the watts. We know that 1 horsepower is 746 watts. And the other thing is that once we know that once we have a ratio of powers, we know the efficiency. Remember, in this case, they're giving you the efficiency. So let's start by saying, okay, the efficiency is the power output divided by the power input times 100, yeah, because it's a percentage. This right here is 75%. So what is our power input? First of all, 0.75%, which is this efficiency, is the power output is 2 horsepower. Okay, that when you look at a motor, it has a motor plate, and it will tell you the voltage, the current, the horsepower, the phase, if it's one phase, two phase, etc. That is the output. So we're simply saying efficiency equals to the power output divided by the power input. The output is 2 horsepower. Well, but in simply have to translate that to watts. So 2 times 746, and that is 1.3. What is? Let me see if I have a calculator here. 2 times 746. 1492. So this numerator part is equal to 1492 watts. 2 horsepower is 1492 watts. Okay, if we want to find the power input, we simply have to multiply this by 0.75. But wait a second, this is only let me see, 1492 times 0.75, 1119. Okay. All right. Now they're telling us to find the current. So remember, P equals voltage times I. But this is a typo here. 0.8. This should be 0.75. Right? Why? Because power output is equal to efficiency times power in. Power is equal to voltage times current. So voltage is, and this is 200, 220. Oh man, this is full of many typos in this example. So voltage is 220. Wow, okay, so let's do it this way instead. It's gonna confuse us even further. So the output is 2 horsepower times 746. Yeah, we said that the 1492 points times 175, we said that that was no, here's another thing that I have a mistake here. Go up. It's not like this because it's, sorry, so it's 0.75 times power input equals 1492 watts, right? Yes, because this is multiplying. A power output is lower than your power input, right? It has to be lower, otherwise you will have more than 100% efficient, which is not possible. All right, so, and this case, we're going to have 1492 divided by 0.75. 1492 divided by 0.75. There you go, 1989. Power input equals 1989 watts. Okay. If the applied voltage is 220, what is the input current? So this is wrong. There are typos here. If the applied voltage is 220, we're very simple. We're going to use this formula. And they're talking about applied, so Pn, so this is E, in. So Pn is 1989. Whoops. I don't know how I did that. Okay, 1989. Remember, we're doing P equals voltage times current, the formula for power. And voltage is 120 times current. So 1989 divided by 120. Sorry, 220. It's not 120, the problem says 220. 1989 divided by 220 is 9 amps. So current equals 189 divided by 120, which is 9.04 amps. Okay. If we wanted to do this in horsepower, the input horsepower, it will be 1989 divided by 746, because 1 horsepower is 746 watts. So 1989 divided by 746 is 2.66 horsepower. 2.66 horsepower. And 2.66 times 0.75 equals 1.9. Yeah, so 2. Alright, so we got the output is 2 horsepower, and it's because it's 75% efficient. Alright, this is the value. I'm sorry about the typos here. Many typos in this example. Another example. If the efficiency is 0.85, determine the output energy applied if the energy input is 50, if the applied energy is 50 joules. So now it's telling us in terms of energy, not power, and it's the same concept. Energy could be power divided by power, current divided by current. It's just a percentage of the input versus the output. So the efficiency is 0.85, and the input is 50 joules. So 0.85 times 50 joules is 42.5 joules is the output energy. And another important concept to remember is that when you have systems together, so say this is an engine, you have your transmission, or sorry, this is a car, you have your transmission, you have your V8 engine that is going up and down the pistons with friction and such and such, and then you have your transmission, etc. Notice that this is another thing that you have to remember. The total efficiency is not adding up, it's multiplying the efficiencies. So even if your subsystem is pretty efficient, your total efficiency is not going to be as high anymore, because assume that your transmission is 0.9% efficient and your engine is 0.85% efficient and your suspension, I don't know why I said transmission again, your suspension is 0.85% efficient. If you multiply 0.90 times 0.85 times 0.95, that will give you 0.727 or 72%. So notice that everything was 85, 90, 95. It was high enough, was pretty efficient, but your total efficiency is only 72%. And that is what happens in cars. Cars are usually between 50 and 65% efficient because have so many subsystems that the total efficiency starts decaying. So the total efficiency is multiplication of every efficiency for the subsystems. Now, in terms of applying circuits for real-life applications, we have breakers. This is what I was telling you when you work in electrical setup at your house or an office, always turn the breaker off, because those will basically it's a switch. This is a huge switch that will cut the power off for your rest of your circuit. A fuse is a very important safety um, element. When the current increases more than what you need to have, the fuse will break. It's also like this symbol, and it will break when you have more than the current that you are allowed to have through your washing machine or whatever, and then you know that something's wrong. It's better to replace a fuse that is a couple of bucks than a whole TV or a whole machine that is thousands of dollars. For your outlets, and this is AC now. This could be DC or AC. This could be DC or AC, mostly AC though. And this is definitely AC because you have your ground, your neutral, and your line or hot. You usually have reset or test to see if the circuit if the power is working. And this is just always live, so you pretty much, this is picture a circuit with a resistor when you have your power, and then you just plug into your resistor for the load. So now the load is whatever is connected to this. Okay, this is your ground again, neutral, line. Now we have contactors. These are used for high voltage, high current applications. Sorry, this is not a contactor. This is also a circuit interrupter. This is another type of breaker. Looks like a contactor, but it's different. A contactor is also like a relay, like a switch. This is also like a breaker. So all these items are used for application of circuits. When you'll see those in most of your house or office circuits. So let's do one more problem. If the current through 100 kilo ohm resistors 3.5 micro, this is micro, this mu is microamps, 10 to the negative 6. What is the voltage drop across this resistor? So very simple, just Ohm's law, V equals IR, 3.6 10 to the negative 6 times 100,000 is 0.36 voltage or 360 millivolts. Another one, if an electric heater draws 9.5 amps connected to a 120 volt supply, what is the internal resistance of the heater? This is Ohm's law too. R equals V divided by I, 120 divided by 9.5, 12.63 ohms. And B, determine how much energy in joules is converted if it's used for 2 hours. So 2 hours into seconds is 1 hour is 60 minutes, and 1 minute is 60 seconds. So 2 hours is 7,200 seconds. 1 hour is 3,600 seconds. 2 hours would be 7,200. And then we know that power equals energy divided by time. So 12 volts, power equals V times I. So 120 times 9.5, it will give you power divided by time. So times 7,200 will give us joules. So in other words, 120 times 9.5 times 7,200 seconds is 8.2 megajoules. 8.2 times 10 to the 6 joules. Very easy. Please review and ask me if you have questions. Let me see. This is the last problem. So this one could be a good one to review. The electric bill for a family for a month is $120. A, assuming there's 30 days in that month, what is the cost per day? So simple, $120 divided 30 months is $4 per day. B, based on 15-hour day, or meaning they only used 15 hours in average electricity for the day, what is the cost per hour? So they didn't tell us what is the cost per hour. Yeah, $4 per day. We're right here. $4 per day divided by 15 hours per day is going to be 26.7 cents per hour. So this will be 400 cents. $4 is 400 cents per day, and divided by 15 is 26.7 cents per hour. Okay, so this is the answer. C, how many kilowatt hours I used per hour if the cost is 12 cents per kilowatt? So if from B was what is the cost per hour, 26.7 cents per hour, but they're saying if the kilowatt per hour is 12 cents. So one thing is the cost per hour, and so this is the cost of using electricity. In other words, if the bill was 120 in 30 days, it was $4 per day. And now $4 per day, if we only used 15 hours, meaning that we're paying 26.7 cents per hour. We're paying that. But now, if the cost of each kilowatt per hour is 12, then how much power are we using? So this is kilowatt per hour, remember? So 26.7 divided by 12 is 2.23 kilowatts per hour. Okay? Makes sense? So cents divided by cents, hour divided by hour, and it will be 26.7 divided by 12 is 2.23 kilowatts. Okay? And then D, how many 60-watt light bulbs, 60-watt light bulbs are pretty standard light bulb, could you have to use if given that energy per hour? So if the total energy we use is 22.23 kilowatts, and we have 60-watt item consuming that, the result is 37.17. So assuming there's no loss or anything, we can have 37 light bulbs. All right, this is pretty straightforward. And to review one last time, if the bill for the month was 120 and the month had 30 days, then we are paying $4 per day. If from each day, in average, we used 15 hours because it's an office, say we closed from 10 p.m. to 7 a.m. So that's 15 hours that we're open. So if every day we used 15 hours electricity, that means if we're paying $4, it's basically saying that 400 cents per day divided by 15 hours per day, we're having to use 26.7 cents per hour. So we're paying 26.7 cents per hour, but we don't know how many kilowatts we're using. Well, that depends. How much is each kilowatt? It's 12 cents per kilowatt. Okay, so it's 12 cents per every 1,000 watts. So if it's 26.7 cents per hour, and every 1,000 watts is 12 cents, then we're using 2.23 kilowatts. And lastly, if we're using 2.23 kilowatts, how many 60 watts load or light bulbs can we use? Well, 2.23 kilowatts divided by 60, or 22, this is 2,230 watts divided by 60 is 37.17, or 37 light bulbs.